So I like to set this up so that these vectors are a little bit larger. So what happens in general around a magnet is the field of these magnets will exit out of the north side of the magnetic pole and will circle back around to the north side of the pole. So the south side of the pole. So the field is going to go in such a manner. So in your book, or in this direction. So in your book, you'll probably see some field lines such that the field lines go away or outside of the north pole and fold back into the south pole. So if you've ever seen those, and I'll show you a quick little video to help you visualize that as well. Okay, you're going to also have this little setup as well, where again you have a compass, and from this little setup, what this is you have current flowing through these wires here, and based on how much current and the polarity in which the current goes through here, well, depending on the rotation of the current is going to determine the polarity. So if I rotate the current, as you see here, maybe if I'm looking from right to left, it looks clockwise to me. The field is going to go in a certain direction, right? So the magnetic field is going to be induced to go in this direction, to the right. So it repels and comes back around. If I change the polarity or the direction, you'll see the direction of the current in the opposite direction, and as well the field lines will reverse. So kind of pay attention to those red lines there, and as I change or flip the polarity of the battery, I flip the direction of the current, and the current is assumed to be going around a coil. You can also see that the compass changes its direction as well. So a lot of these questions I'm going to leave you guys to answer. Go through this. You need to make sure you read. This is probably why you need to maybe give your group a little bit of time so that everybody can read this. But let's talk about this formula right here. I have it on the board as well. As soon as I stop sharing my screen, we'll talk about that. So with this formula, pull this up a little bit for you guys again. This formula for B here is going to give us an understanding of the strength of the magnetic field. So you guys will probably already know that B is going to be a measure. The unit's going to be in Tesla, just like the car. Mu naught is a constant, and this is called the permeability of free space. It's not like that same concept that you had when we did Coulomb's law. Kind of sounds the same. That one's called the permittivity constant. This is called the permeability constant, and we use mu naught to figure out that value. Again, it is a constant. The handout allows you to use this as a unit value. So 1.26 times 10 to the minus 10 newtons over amperes squared or amps squared we can use. But you'll see in a minute that we can also use 4 pi 10 to the negative 7 Tesla meters divided by amps on the bottom. Again, you'll see it as soon as I change my screen. You might be able to see it right now. I'm not sure what you're seeing right now. Okay, so, and you'll also see a minor mistake that I made that I looked up at because I'm so cognizant of units. You'll see what I'm talking about in just a second. All right. So these are questions that you're going to need to answer. I think these are fairly straightforward. You're going to put, once you get to the simulation, you're going to put a meter at these three spots on the page. Your answers should vary now. So depending on what your setup is and how you set up the system, these answers may vary slightly. So just be cognizant of that. There should be some pattern that results from this. You're gonna make some observations. Like I said, you're gonna look at this as your second simulation. Okay, so here's a minor mistake, and I'll put it in the notes below. The field strength B, this unit G, I'm not sure how that got in there. That should be units of Tesla T. So let's put that in the notes down below. So page 7, table 1. Units are Tesla. The unit should be. So your field strength is going to be based on, and that right there should be, it's going to bother me, so I'm sorry, I got to do this. So data table 2. It needs to be in Tesla. Okay. So your field strength will vary, obviously, as you modify the voltage, and you're going to just simply plug in those numbers. So this is more of an exercise that you just kind of playing around with the simulation, but I want to kind of give you an idea and understanding what this looks like via more of a simulation. Now, the words are a little hard to see at the bottom here, so I'll read this to you. So just kind of follow along at the bottom if you can, but I'm going to read this to you. So it says if current flows through an electrical conductor, it is surrounded by a magnetic force field. The force field is clarified by force field lines. If you wind the wire in a coil, you will observe the following. Essentially, it's going to produce some superimposed magnetic field. So the magnetic forces are superimposed, and the resulting magnetic field is similar to that of a bar magnet. Where the force field lines emerge is the magnetic north. Where they enter is the magnetic south pole. Remember, that's what I was talking about in terms of the direction of the lines.
This
Oh,
is a metabolism killer. This.
all right, sorry. All right, so there's one good simulation, because it's kind of hard to visualize some of this stuff doing this online, and we put this class together during COVID times, and we're still working on some various bits and pieces here. I wanted to show you one more. It's just a quick little short from YouTube, um, where you will see this guy, and I wouldn't suggest the technique that he uses here, but it's a little blurry. But at the very beginning, you'll see him wrapping up this wire around to make a coil. It creates a coil. Gonna place it. Wire here, like on the top of it. So we're gonna place it on some kind of power source to produce the current through, and it's gonna take some iron specs showing you how this magnetic field is produced. Tap it. See some of those magnetic field lines. It doesn't tell you exactly, doesn't show you exactly which direction north is, but it gives you some sense of how this can produce a magnetic field. So if you take a wire, you wrap it around X number of times, you can produce a magnetic field. And so if you've ever torn apart certain items, like every once in a while, I'll tear apart my clippers. I cut hair, and so inside those clippers, you can see a magnetic wire, and inside of it, it produces some sort of magnetic field from that once I turn it on and apply an EMF to it. So, and then finally, in what we do in class here, let me stop sharing. What we do in class is we produce an EMF using this thing right here called a tangent galvanometer. Right. So the wires are a little bit more cleaner. So you can see around here are wires that are wrapped. See that? Really fine wires. We can use either 5 of the loops that are in here, 10 of the loops, or 15 by plugging into any combination of plugs in here. So if we plug into, let's see, I think it's these two plugs, we can use 5 of the loops. If we plug into these two middle, we can use 10 loops. And if we plug into these two outside, we use all 15 loops in this wire piece. We apply a voltage to this, which creates a current, and we can produce a magnetic field within here. And what we do on top of that is we figure out the magnetic field of the Earth. It sounds a little complex, but it's not really. What happens is once we produce a magnetic field, the compass, we put a compass inside here, doesn't work. This is not the best class to do it in because there's a lot of electrical currents in here. First time I did this, everything went haywire because I didn't realize how many electrical panel boxes we have in here. So if you're gonna repeat this, or if you're ever you know, going to teach this class, you got to make sure there's not a whole lot of interference around you. So anyway, we put a compass right here. It sits right here. We apply a current. It will deflect, and we can basically, by virtue of taking the summation of the two magnetic fields, we can figure out where magnetic north is. All right. I know that's a lot, but it's not as difficult as what it sounds. Okay, so on the board here, we have, and I know it looks a little bit blurry here, but I did my best. We have a current that is going through a wire. I didn't bend it in any kind of way yet. We have a current that's going through the wire, and what it's going to do, we're going to produce some electrical field. And so how you determine the electrical field is via the right-hand rule. You're going to use your thumb, right? And you're going to point your thumb in the direction of the current, and you're going to rotate, and that should tell you the direction of the magnetic field around this wire, right? And then when we kind of loop it even more, all those little loops, if you will, produce that magnetic field. So we start you off by looking at it in the straight wire, and then we bend the loop as we did, as you saw in that simulation. So the way if this were a three-dimensional version of this, the magnetic field would first come out of the board, and then it would go back into the board. So this is supposed to be your 3D version of that, and the way your hand turns in this direction is the way that the magnetic field is turning in this area here. Okay. Now to determine the value of a magnetic field given a coil of some kind, we have to look at this formula, and this formula is called not give it to you, it goes by Biot-Savart's law, and it basically says that if we multiply some constant, which is this permeability of free space, which I wrote down 2 times for you here to help you understand, give you some options in terms of how you're going to solve this.
Is the A variable for area, or is that in amps?
Yeah, I'm gonna go through that here.
Okay.
So this N right here, you probably can't see all of that. I put a script N right here. Right? And the reason I put that there, I didn't realize that the script N could be confusing with N for newtons, right? So this N right here corresponds to the number of coils. Is that what you were asking, Mr. Eulia?
Well, I was referring to the permeability of free space. Like it's units. It's units. M over A, are those units? T times M over A.
Oh yeah. So this is Tesla.
Meters and amps.
Yep.
All right, thank you. I was just confused because it's like all over A, so it could be like area.
Yeah, I know. That's why we got to really be clear. Whoops, maybe you said it and I almost wrote it. This is amps.
All right, makes sense. Thank you.
Right? And over here, this is newtons. Now I just wrote this on the board, right before class, and I poked my head up. And really, what I probably should have done instead of script N, I probably should have written little n just
Excuse me,
for
Professor, I have a question.
clarification. Yes, sir.
If it is amp, shouldn't it be I instead of A for intensity?
No, no. In this situation, we're using A for amps.
Okay.
So let's see. I was using what we had in the handout. I want to make sure everything is. So I is the current. So we can't use that all over again. And no, this is correct. This is correct. So what you're going to plug in here, though, are going to be units of amps. I is the current there. Okay. So I is the current. Let's write that down. It's going to have units of amps. N is the number of loops. U dot has those units. You can pick your poison as to which one you're going to want to use. And L is the length of the wire. So what you have to figure out, if you're creating these loops that look something like this. So let's just say I have 3 loops. If I have 3 loops, let's just take this back a little bit here. I need to figure out how far this current is flowing. Well, assume that these are circles. And figure out how far it is through one loop. How would you figure out how far it is around one loop, class?
2 pi r.
2 pi r.
Wait, that's for L, right?
Correct.
Okay, so L is the circumference, okay, of one loop. All right.
Basically, the length of the solenoid is essentially the number of revolutions that a current might go through. Okay, so
Wait, so length of solenoid is like all of the loops or just one?
all of the loops.
Okay, thank you.
Because remember, I'm taking a wire, just like you saw in that picture. I'm taking a wire and I'm creating all these loops. Right? So either you're going to need to know what R is, or it'll be given to you. Now, I don't think for purposes of this lab, you'll have to do all that, but it's going to be probably good information for you in your lecture. This one is more of a hands-on lab. You'll experiment. You'll figure out which direction the magnet is pointing, the magnitude of the magnet. The meter is going to give you the magnitude of the magnetic vector in 2 directions. So if in the x direction, let's just say it's 10 Tesla, and in the y direction it is 10 Tesla, its magnitude is going to be a combination of those two. So it's the sum of 10 Tesla and 10 Tesla. So you would just trying to make sure I'm staying on the screen here for you. It would be this B vector here. Figure out the B vector by taking the sum of the squares, square root it. So 10 squared and 10 squared, so 100. Square root of 200. Let's see. is 14.4. 14.14. That's it. So B would be the magnitude of the B vector at that particular point.
And for the direction, we do like the tan theta equals y over x.
Say that again.
For the direction, we do tan of theta equals by over bx.
So the direction of it is going to be, I'm not going to ask you to do a lot of that kind of calculation. You're going to need to use the simulation. The simulation should give you some kind of indication as to which way the direction of the vector is pointing.
Okay. I also have one more question.
Sure.
So L is 2 pi r times n, right?
Correct.
So when you plug it into that formula up top, don't the n's just cancel out and you have mu times I divided by 2 pi r?
Correct. So some of these formulas you'll even see where 2 pi r is incorporated in this as well. So if n is equal to, yep, you can look at it that way as well.
All right, thank you.
So there's all different variations on Biot-Savart's law, but this is the one just kind of working off of what you have in your handout and going from there. Right. So we're just trying to make it as simplistic as possible. You definitely need to know something about the right-hand rule. I can almost guarantee you that this picture is going to show in the way I teach it when we have two vectors and show you which direction. I think of a jar of some kind, assuming that it's a standard jar. And if you loosen the jar, the top is going to come up, right? Just like this rotation. So the jar is going to come up, the top of the jar is going to come up. If you tighten the jar, it's going to go back down, and that'll tell you the direction. That could also tell you the direction of the current as well. Okay, so again, as I said, make sure you look at those. I talked about a couple typos to some. You also need to look at who's going to be in your group. I'll send you guys a quick little note letting you know that I put together everybody. It should be the same as what you've had in the past. Make sure you understand who's in your group and whose task it is to do what. Set a deadline. Make sure you have that deadline. If it's the Thursday before, if it's the night before, the group has to come to that understanding. I don't know everybody's schedule, so it may not be cool for everybody to wait till Thursday morning, because you may have some of you guys may work Thursday morning. May not be cool for you guys to set that as a deadline. You guys determine your deadline. I don't determine that deadline. Your group needs to determine that deadline for you. Okay. It just needs to be submitted by next week, midnight. Okay. Any other questions before we sign off?
How do you know the direction of the magnetic force when it's coiled up?
How do you determine the direction? The direction is going to be determined by well, for our simulation, we're going to use the compass to determine that direction. So the direction is always going to flow out of the north side, and it's going to flow back over to the south side of the pole. Does that make sense? So it's going to follow those little circular patterns that you saw in that last simulation, that short. That'll give you the direction of the magnetic flow. All right. The thumb that I showed you here is going to be the direction of the current, though, on 4 straight lines. Does that answer your question?
Yeah, thank you.
You're welcome. Okay. All right, so that's my time. If you have any questions, I should be getting you guys reports back. I should have about 2 of them done, just in the queue. So stand by on those. All right, you guys take care.
Thank you, Professor.